Hi, my name is Mark Lewis. I'm co-host of Café Scientifique, and great to see you here tonight. Some people are good mathematicians. Some people are good communicators, but it's very rare to have both. But such people do exist. And as a case in point, I'm very happy to introduce Trefor Bazett. And he describes himself as a person with a passion for education, but a side interest in algebraic topology. And I think you'll hear about both tonight. He's an assistant teaching professor at UVic, and he has a Dr. Trefor YouTube site with over 500, or almost 500,000 subscribers. So that kind of tells you about his communication skills. And he has changed the attitude of many people about mathematics, and also helped so many people at the university gain skills in mathematics. And he'll tell you more about that. And he's won very many awards for math education. Most recently won last year from the Pacific Institute for Mathematical Sciences for his education work. So you're in for a real treat tonight. Please welcome Trefor Bazett.
Thank you so much, Mark, and thank you everybody for being here. And I'm sorry to do this, Mark, but you said one thing incorrectly. No fault of your own. You didn't know this. He asked me to send my CV so he could read it through. But it turns out that I got the news a couple hours ago that I am not an assistant teaching professor. I have just gotten tenure, and I am now an associate teaching professor. So hopefully a pleasing error to make. So it's very nice to be here, and I'm very excited to talk about math. Hands up, has anybody forgotten any math in their time? Okay, put your hand up if you are still able to count to 2, though. That's what I need for this talk. Can we count to 2? Okay, you're gonna be fine, because I know math can cause a lot of anxiety, but that's totally okay. Now, for me, it causes anxiety because I do YouTube, and YouTube is a visual medium, and I'm here on the stage without my videos behind me. So I have a box of props. It was the closest thing that I could actually do to be making a video, and I wanted to introduce this idea of algebraic topology. It's a weird buzzword, algebraic topology. I want you, if nothing else, to know what is algebraic topology by the end of today. And very loosely, we're going to be studying shapes. However, lots of people study shapes, like people who are interested in geometry study shapes as well. And in geometry, you might care about measuring the distance between some points. You might care about having an angle between two lines and calculating those very precisely. I also study shapes, but I study it much looser than a geometry does. I don't care about angles, I don't care about distance. You can imagine everything in my world is made out of Play-Doh or out of rubber, and you can stretch it and manipulate it around. And I'll show you why I might care. So here I have, this is all a tangled knot. Here I have a knot, and I can play with this knot as much as I like. I can move it around, I can try and manipulate it. But I think we can agree that this is the same knot no matter how much I go and wiggle it around, no how much I reorient it in space. This knot could be made out of a rubber band and I could pull it and make it bigger, I could compress it and make it smaller. As long as I don't come along and cut it and retie it, I think we could agree it's the same knot. So this is what I mean about the difference between geometry and topology. I want to study what is intrinsic about this weird shape, this knot that I can't seem to get undone by just wiggling it around. And I only care about the intrinsic properties that are embedded in this particular shape, not how specifically it's oriented in our universe. Okay, so now I want to ask all of you a question, and if you read the sort of abstract for this talk, I put it in there, but I'm going to ask it now. This I stole from my daughter, and if you can see, it's a straw. It's got a hole that goes through it, a hole, or possibly more. So my question for all of you, and we're going to need a show of hands in a moment, but I want you to think, how many holes does this object have? I've heard people argue to me that it has no holes, that it has one hole, that it has two holes. Maybe someone will be able to argue something different. So do you have it in your mind what you think you're going to guess? Oh, infinitely many holes. Okay, that's a good one. Okay, so let's raise our hands for, you know what, I'm going to ban infinitely many. It's too many for me to think about. I said we could only count up to two, right? Hands up if you're on team, this is two holes. Oh, okay. Okay, what about hands up team one hole? The other half of you, any brave team zero holers? Okay, okay. Oh, is waving a hand a half a hole? I'd be excited if that was the answer. No, there's something else that's fun about my daughter's toy, which remember how I said I don't care about lengths or distances? Like, I can stretch it. Right? Isn't that not a good toy? Yeah, it endlessly amuses her. Oh, okay. Well, you know what? We'll have to take a little while putting it back down. Yeah, this is a jazz club. I feel that's what we need. So the point is that can we at least agree that I haven't changed the number of holes, right? If I rearrange it in some way, that's all the same thing. This is going to be brave. If I take off the wedding ring, that's all the same, right? Whether we think 0 or 1 or 2, it should be the same answer for all of them. And so you can imagine, well, I can push this down a little bit. I could sort of keep on pushing, hopefully, until it was as squeezed as possible, almost like infinitesimally thin. That's a possible answer. So maybe I haven't convinced you about 1 or 2 holes yet, but this is just the first thing we're going to talk about. Because I got a balloon here. And even better than a balloon. So you can think in your mind, I won't quiz you, but how many holes does this have? Also 0, 1, 2, half, or infinitely many? Okay. And then this is my next favorite one. Okay, the best thing about my daughter's toy. Okay, now that's just getting annoying. You can come around and put it together like this. So now it creates a sort of loopy thing which is going on. So now we got to wonder, how many holes does this have? So try to make your predictions that you have in your mind. Okay, so we clearly need to start somewhere if we're going to answer what is this issue of the number of holes. Okay, what else do we got in here? can we make an agreement that this is just a piece of paper? This has no holes in it, right? Everyone's okay with that? Okay. It's got a hole now, right? I can put in one hole, and by my rules of stretching, remember I said that we can sort of stretch things, imagine it's made out of rubber, imagine it's out of Play-Doh, that's all the same for us. Like I can come along here, I can make it a little bigger. Let's come on. Okay. So now we have this object where it started with no holes, I came and I punctured it, and now it certainly has one hole. So hopefully we've agreed on that, okay? So how many holes does this have again? Lots of people like one, the hole in the center. And maybe you could think, so if you're saying if it's got one hole right now, and I come along, I'm going to do this very carefully. I'm going to add another hole. So it starts with one in your mind, all the people who thought one. Okay. Oh, I really want, don't worry. I planned for this. There's a way to do it that doesn't make it explode, but that one exploded. Okay, one sec. Oh, my testing. You know what? It's good enough. Doesn't matter. Perfect. When I tried this before, it worked out a little bit nicer. This is a portion of the balloon, but this is what I want to hope you think. If it didn't explode so violently and aggressively, I think it would have appeared something like this anyways, right? So this is just a small portion of my balloon, but the point is that I put a hole in the balloon, and when you do that, it all sort of goes apart, and what you are left with is a disk, which had no holes. So one second. I need to understand this correctly. We added a hole to the thing, and when you added a hole, it ended up with 0 holes. So does a balloon have -1 hole? So I think this is the argument I think we're left with no other conclusion at this point. A balloon has to have -1 holes. It started with whatever it was, you added 1 hole to it, and that took us all the way back up to 0 holes. A balloon has -1 holes. I think I must have convinced you. I destroyed my backup, so we're gonna have to do this again. I'm not gonna pop this one this time. So while I'm blowing up the balloon, just try to reflect for what exactly is a hole? That's what I want you to kind of think about here. Oh. This is my last one, so I'm going to keep it nice and small. Okay, so I'm going to try to give you an idea of what I mean to myself when I'm talking about a hole. So I have my balloon, and I'm going to draw on it. I've got my little Sharpie, and what I'm going to draw is I'm going to draw a little loop. So I've drawn on this loop here. And the way I think about this is this loop, I call it one-dimensional. I know that this loop is living on a balloon, which is living in 3-dimensional space. But if I was an ant and I was living on the loop, I could go forwards and backwards. There's only one dimension that I have here. So I'm going to call this a one-dimensional loop here. And then we talked about how this idea of I'm a topologist. I can be all wiggly and wobbly. Like I can stretch things and move. Like I could take this and I could make this one. I could move it in and that'd be fine, right? I could move it in and I could maybe actually, no matter what loop I drew on here, I think I could go and sort of contract that loop down to this particular point. Even if I drew the equator, if I imagine that this was a piece of rope going around the surface of the Earth, let's say, I could imagine slowly slipping it up as it goes all the way along until it collapsed down to this point. This is In contrast to what happens on, oh, she'll be sad if I draw on this one. So let's put the Sharpie away, not cause any more problems. That's in contrast, but just imagine that I had drawn a loop around this way. If I had drawn a loop around here, I can't contract it the same way that I could with that balloon, could I? There's no way, I mean, I could move it to the other side, but I can't ever get away with it. Same with, how do I open it? Same with this one here. If I drew my Sharpie right around there, I could take that loop and move it all the way down to the other end. That'd be fine, right? Like I could slide a loop from all the way to the end. I'm sorry to crush the dreams of all the two-hole people here. But if you call this one a hole, I could slide away and get all the way to the other end as well. So this leaves me, oh, and I'm going to do if I have my disk here or my annulus here, I could also just as easily imagine a loop here going around. Let's see if I can draw it. Something like this. Again, this is another idea. This loop, I can never make it go away. It could get smaller and smaller and smaller, but the hole in the middle is blocking that loop from shrinking all the way down. So here is my notion of a one-dimensional hole. A one-dimensional hole is when you draw a loop, which is one-dimensional. There's something missing inside of it. It's the boundary of emptiness. That the hole that I have here, the boundary of that thing that is missing is a one-dimensional loop. So I'm going to call that a one-dimensional hole, and I'll claim that my answer to the straw question, because I could take the hole at the one end and loop it all the way around, is that there's one hole in a straw. In contrast, if I'm talking about the balloon here, well, the balloon doesn't have any one-dimensional holes to it. If you try to draw a loop, I can close that loop up no matter where I draw it. And if you try to put any loop that you like over here, I can sort of all imagine it shrinking down to a point. I'm going to say it doesn't have a one-dimensional hole. But it does have a two-dimensional hole for the same kind of argument. There's an emptiness in the middle, and the emptiness in the middle is surrounded by this two-dimensional object, which is the side of the balloon. Now, again, you might think, hold on, two-dimensional, this is living in three dimensions. You know, but if you imagine living on the surface of the Earth, you can go north-south or you can go east-west. If you're an ant that lives on the balloon, just as we're sort of ants living on the Earth, if you will, you only have two dimensions. So I consider this balloon, just the shell of it, to be two-dimensional. This I will call a two-dimensional hole. Okay? So let's try and analyze which one we want to go to. Let's try to do, no, okay, we'll do that one later. Which do I want to do? Yeah, I want to do this one. This is fun. Okay, so this is going back to this shape here. Let's try to answer what kind of holes it has. Certainly, it's got this hole that loops around here, right? That I will call a one-dimensional hole. If I drew this one here, can't get rid of it. So this is a one-dimensional hole. It has a second one-dimensional hole there. So I think it has two one-dimensional holes, and it's enclosing some air in the middle of it, right? So it also has a two-dimensional hole. So this object, in my mind, let's make sure we're all on the same page, has two different one-dimensional holes, the loop that goes around this way and the loop that goes kind of around this way, and a two-dimensional hole. It encompasses some volume, which is in the inside. Okay, I'm going to be really annoying at this point. It also has a zero-dimensional hole. I need this for technical reasons. Mathematicians do this kind of stuff all the time. They're talking about one, they're talking about two. What is zero dimension? Zero dimension is just a point. And I'm going to say every object has a zero-dimensional hole, just to make my math work out nicely, okay? So You have a one-dimensional hole, the mic has a one-dimensional hole, this is a one, everything has a one-dimensional hole. If there's something to it, it's got a one, did I misspeak? A zero-dimensional hole. Everything has a zero-dimensional hole, okay? Okay, let's go and play around with a couple other ones. Okay, which one am I going to go for next? Yes. So this is my daughter's pair of pants. I'm just stealing everything from her. Okay, what do we think? Can I make you do work? Can I make you talk to each other for a second? Okay, you have to find your neighbor. How many holes does this have? And, are you ready? That's question one. If I sew her pants together and create this, how many holes does that have? Okay, so that's your homework. Can you chat with your neighbor for 2 minutes, please? Okay, thank you for your buzz. So let's take the standard pair of pants. Anyone want to be brave and tell me what they think? Oh, that means I've given a good enough one. Someone's got to be brave. What do you think? 3 holes. It's a very good guess, right? There's something at the top. Everything's a guess. Something at the bottom, something at the bottom. 1, 2, 3, right? 3 cuts. What do you think? One two-dimensional one. Yeah, okay. Although in this case I can whoa, that was weird, stick my arm the entire way through. So this one, the type of holes are a bit different from the balloon, aren't they? The balloon, there was this region I could never get to. I can get to the region inside of it. I can get to the region. Okay, so I also stole from my son. Don't tell him about this one. To make it easier, a pair of pants and a pair of boxers are the same thing for a topologist, right? You just cut the pants a little shorter. Okay, so let me see if I can illustrate one way to think about this. So I'm just going to keep on doing the topologist things. I'm going to keep on pulling stuff up. This is just, it's all made out of rubber, right? I can stretch it whatever I want. Okay. So now I'm going to hold it like that. That's a disc with 2 holes. Is it not? 3 was the tempting answer. 3 is the tempting answer because you can clearly see there's something cut at the top and there's something cut at the bottom and there's something cut at this bottom. But it runs into that same problem, which was that if we thought a straw, which had 2 cuts, was only 1 hole, it turns out this thing with 3 cuts, when presented this way, has 2 holes. Okay? So mathematicians try to play around with this, and one of the things that we would like to be able to do, I'm sorry, I'm going to put the underwear away, is come up with, if you give me an object, and you give me an object, and they look visually different. Your object is very stretched. How do I know whether you have the same object or whether you have a different object? And I'm playing around with small things, but maybe you want to imagine that you're in some very high-dimensional space in some weird machine learning algorithm, something where it really matters, and you've got these 2 different objects, and you're asking the question, are they the same or are they not the same? So in mathematics, we have an idea called invariance. An invariant is something where I'm going to look at these 2 objects and I'm going to compute a thing, And if the thing that I compute is different, the two objects are definitely different. It provides a way to tell them apart. So I'm going to give you one example of an invariant. It has a fancy name called the Euler characteristic. Euler is a very famous mathematician. He had his fingers in a huge number of different areas of mathematics, including topology, but definitely not just that. And here's what he said. Add up the number of even dimensional holes and subtract from that the number of odd dimensional holes. This was why I needed that weird zero-dimensional hole to do the even one properly. Remember I said I needed it for technical reasons? This is why. So we're going to take the number of even holes, and we're just going to subtract the number of odd holes. And then the big theorem says if that number is different, the two objects have to be different. Okay, so let's go back to the pants. We had argued that this has, okay, it's got a zero-dimensional hole, right? Everything's got a zero-dimensional hole. So that's one in the even camp. We're arguing it doesn't have a two-dimensional hole because there's nothing enclosed, like I can always get through to it. And then we just argued by the pulling it together business. I can't do it as easily with the pants, but you remember the thing that it was the disk with two holes has two one-dimensional holes. Okay, so putting that together, it had one even dimensional thing minus two odd dimensional things. The Euler characteristic of a pair of pants is -1. Okay, let's do it one more time. We're going to be brave. We're going to sew together the pant legs. For a moment, I went to my wife and I said, is there a pair of pants that I can destroy for this talk? I want to cut them off to make them shorter and shorter. And I also want to sew them. And, well, I'm here without such a prop, so you can imagine how the conversation went. This one's interesting. It starts to, okay, it's got a zero-dimensional hole, right? Doesn't have a two-dimensional hole. It kind of really feels like it should have a two-dimensional hole, but this hole at the top breaks it. No two-dimensional holes. It has a one-dimensional hole, this one right here, right? If I draw that loop, I can't get rid of it no matter where it is. And I've now, even though I cut off these, I've added another hole here. So this one actually has two one-dimensional holes as well, so 1 minus 2. This also has Euler characteristic of -1. So somehow, this business of changing from this to that seems very different, but the Euler characteristic was the same. So now there's an interesting question. Okay, I told you, if you two give me different objects, and you can compute an invariant, and the invariant is different, they're certainly different. But if you compute some invariant and the invariant is the same, it turns out this doesn't necessarily mean they are the same. These both have the same Euler characteristic, both -1, but they may be the same object and they may be different objects. So we have to adjudicate this. You can think in your mind, if this was made out of rubber, could I take this and transform it in some non-obvious way? I don't immediately see how I could transform the one into the other. That's our debate. So we still don't know whether these are the same object to a topologist or not. Okay. I came with one more prop. So this is two joined circles. A circle there, circle there. It's got our same Euler characteristic, right? It's got the zero-dimensional hole, two one-dimensional holes, subtract that, -1. Same Euler characteristic. And I think that, let's see if I can convince you. I'm going to go back to this version of it. It's a little hard to visualize, and when I start chopping this up, it'll become easier, but I'm just going to hold it up and see if we can do a good job of visualizing it. Does this sort of look like the same? Like this loop that I'm holding here in my right hand represents this loop. And this loop represents the pant legs. It's just that the difference between the two objects is that this, you have to sort of imagine this folding itself down until it's much smaller. But maybe you can visualize, and it's okay if it sort of seems weird in your mind. I'm going to convince you better in a moment. It looks pretty similar. nevertheless, two joined loops. Two joined loops as well, right? I think it's easier when you do the regular pants to see it. When we saw that a regular pair of pants is a disc with two holes cut into it. A disc with two holes, another way of saying it is two loops. Okay. Oh, I hope I do this right. I only made one of these. Remember how I said I wanted to cut my daughter's pants apart? Well, this is why we have the prop. Okay, so what I'm going to do is I'm going to cut both of my loops in half. This is my favorite part of our demo here. Let's see what happens. Okay, all right. So I cut it in half. It creates, what are these? Who's been arrested before? Okay, nobody knew, so that's a good thing, okay? Yeah. And we're going to cut the other one in half too. Let's see what we get. Okay. See if you can predict what's going to happen. So I've done a bunch of cutting, and we get a square. Right? I get this to the topologist, not to the geometer. Geometer thinks these are very different. I think they're the same thing, right? A bigger hole in the middle. Okay, so I have to tell you what on earth a pair of pants is. Okay. Let's see here. So I'm just going to start without a hole. So basically, we're going to imagine that I'm going to do something on the right hand to this object, but I'm going to just imagine it's easier to show you with the piece of paper, so I'm going to do that here. I haven't put the hole in it yet. Here's how I can make that torus. If I come along and I take the long sides and I glue them together, tape them together, attach them together, I get a straw, right? So I'll do it one more time just to be clear. We're starting with our disc or square. We attach two of the sides together, and now we get a straw. And then what you could imagine is doing is then taking the short sides and also attaching them. So see if you can imagine what we would get. So I take the long sides and attach them, and now it sort of goes bad because paper kind of sucks, but we get to our torus again, okay? So the construction I wanted you to understand is I start with my square, put two of the sides together, you get a straw, put the other two sides together, you get to a torus, okay? So, I have to remember how it was formed. Okay, we're going to fold. Okay, so let's fold it. Let's attach the top. I'm going to imagine I'm going to make a torus, right? So I can attach the top and the bottom together and make handcuffs. And then I'm going to take the sides and move them together and get back to what I started, the two joined loops. Oh, that's not the punchline, but yes, I'll take it. Wait for a moment. You've got to. This is okay. Well, if you're going to like that, you're going to really like what's coming on in a moment here. Okay. So, where we were at was that if I started with a disk, or started with a disk, this is a disk, a square disk, and I folded it up together, I'd get to a torus. Now what we have is that if I start with a disk with a hole in it and fold it up, I get a pair of pants. So what's the answer? A pair of pants is you start with a torus and you pop a hole in it. And now you can do your clap line that you were coming up a little bit earlier again. So this kind of construction is how we make arguments sometime in topology, where we're trying to take objects and represent them in let's say, an object that's new to us and represented in an old way. So this object is one I feel very comfortable about understanding. And I just like doing it, so I'm going to do it again one more time. Make the handcuffs, put it together. Is that the two joined loops that you end up with, which I think we had argued was sort of equivalent to a pair of pants, turns out to be the same construction. I've basically constructed a pair of pants in the same way I construct a torus. I just see that with the pair of pants, I have this hole cut out that's inside of the middle. I'll give you one other way to see it. Okay. Remember, this was the one that was a little weirder, a little less obvious to see that it truly was two joined loops. Like, maybe you'd be willing to disagree with me on that. So what I can do is I can take the waistband, and let me imagine I glued the waistband together. If I glued the waistband together, now I just have a torus, right? So this is the same thing as this. They're the same object. So if I take the torus and puncture a hole in it, that's me opening up the waistband now. And so this object is also what we call a punctured torus. And so hopefully there's a few different ways of seeing how we can play around with these Euler characteristics. Now, have you ever seen, like maybe in computer animations, where they'll take a face and it all becomes like a whole bunch of triangles? Like, actually, the Café Scientifique, even that image that I think I saw, was that a triangulation? I can't remember. The sort of promo image that sometimes happens. Doesn't matter if it is. But do you know what I've seen when you see those sort of computer images where they take something and you represent it in computer graphics as a ton of triangles? The reason I'm mentioning this is that this thing I've talked about, this Euler characteristic, our goal isn't really playing around with small little objects like this, as fun as this has been. The goal is to try and apply this to tell the difference between objects that are very bizarre and very weird, and we would like to know, do they have the same mathematical property or do they have different mathematical properties? And so one of the features that you can do, and one of the things that's nice about math, is if you have a triangulation, like happens all the time in computer graphics, then plugging that into the computer and computing the Euler characteristic is just a very short little program that people can run. So it has this really nice feature. Okay. So now I've given you enough. Oh, maybe I should tell you why I call this algebraic topology. I think we've convinced ourselves about topology. Topology is I'm allowed to stretch things around, and I'm interested in the mathematical properties of shapes where I'm allowed to do this stretching. The algebraic side is anytime you take a topological object and you try to associate a number to it. A number is something I can do algebra on. I can add things. I can subtract things. That's what Euler characteristic is doing. It's a form of algebraic topology because it's putting the rigidity of numbers and sort of math that you can do algebra on into this world where everything is very wiggly and wobbly. And as you go on in algebraic topology, the objects that you're studying are more complicated than the ones we're talking about now, and the algebra you're doing is more complicated than the Euler characteristics algebra, but that basic idea continues. Okay, so I wanted to share some of my favorite theorems that come out from topology. So the first theorem is going to hopefully sound very obvious. I think this is true for everyone in the room. I don't see any babies. Every one of us has at some point been 3 feet tall. Is that right? Like, we were all born less than 3 feet tall, right? We're now, I think, all over 3 feet tall. At some point, that means in the middle, we must have been 3 feet tall. That seems just sort of obvious, right? Now, there's two features about this. By the way, this theorem is called the intermediate value theorem, and it says that an intermediate value must exist. And we teach this to all of our first-year calculus students. They have to come in and learn their intermediate value theorem as part of doing calculus. But that intermediate value theorem is a statement about a couple things. So first of all, it's a statement about my height function. And the word we use this is for that it's continuous. And it's basically the same idea that we're talking about in topology. You can imagine slowly growing your height function, but you don't have a weird thing where 1 second you're 3 feet tall and the next you jump to 4 feet tall, some big discontinuity. That's not allowed. And it's also a statement about the underlying shape. There's this interval of time from when I was born to right now, and that interval is just a line segment. It doesn't have any holes. It doesn't have spots that you can jump for. And those are both implicit. When we say it's obvious, quote unquote, that we were all 3 feet tall at some point, this is part of the intermediate value theorem. Now, that's not so fun, it's just sort of obvious. Let's see if we can use it. Okay, let's imagine we're standing on the equator. We're going around the equator of the Earth. And what we're going to do is, let's not measure height any longer. Let's measure temperature, say. So we're going to measure the temperature as we walk along the equator. Sometimes it's hot. Most times it's hot. On Sunday, I'm taking the kids to Mexico, so I'm very excited. It will be hot, nearer to the equator than it is over here. That's why they don't need their pants, and it's okay for me to bring them. But either way, there's going to be a temperature along the equator. Now, we have in math this word called antipode. An antipode is the spot on the exact opposite side of wherever you are. So if you're on the equator, the antipode is the opposite side of the Earth if you go directly through. So let's imagine I measure my temperature at one spot. Let's say it's 25 degrees. And you measure the temperature on the spot on the opposite side of the Earth, and it's 30 degrees, say. Well, my claim is that as you go around the equator, as you compare your temperature to the temperature on the other side, somewhere there must be a spot where the temperature at the location you're at and the antipode are identical. Not both 30 degrees with infinite precision, if we were imagining it in mathematics, literally the identical number. And I can prove it to you, hopefully. So let's say, what do we say, 25 degrees here, 30 degrees there. Let's take the difference between those, kind of like we did with the Euler characteristic. Remember we were doing even minus odds before? Let's take temperature where we're at now minus temperature where we were on the opposite side. So 25 minus 30 would give me negative 5. Okay, now let me flip around. I'm going to go all the way around the Earth. So now I'm over here and the antipode's over here. So now I'm at the 30 and the antipode's at the 25. 30 minus 25 is plus 5. So at this location, the difference was minus 5. At this location, the difference was plus 5. By the intermediate value theorem, remember there has to be all those intermediate values. There must be a spot where the difference in the temperatures is 0, where this spot and this spot have the same temperature, so their difference is 0. So I've told you a theorem, the intermediate value theorem, and then a consequence of that theorem, which is this thing about equators that's all weird. But it goes further than this. Let's imagine now we don't have to be on the equator, we can be anywhere on Earth. We're going to still consider the spot like here in Victoria. Does anyone know what's the antipode of Victoria? Or is it somewhere in the Pacific? Is it in Asia? It is in the ocean. Yeah, okay. So somewhere in the ocean. So we're going to look at our location here in Victoria and somewhere across. And then what we're going to measure is not just temperature, but temperature and pressure. So we've jumped from a one-dimensional circle to a two-dimensional sphere. And we've also jumped from one property that we're measuring, which is temperature, to two properties that we're measuring, temperature and pressure. The theorem is still true. There is some location where that location and the antipode have the identical temperature and pressure at the same time. This must always be the case. Now, it could be the case that there's many of those, right? There could be many, many points that have the same as the antipode. But the theorem, this is called Borshak-Ulam for those who are interested in their Wikipediaing after the talk, this Borshak-Ulam theorem guarantees that there is at least one spot where the temperature and pressure is the same as the temperature and pressure on the other side of the Earth. Okay, I have two choices here. I guess the question is, should I take my belt off in front of all of you or not? Or the other theorem? Okay, 1 second. I have to see. Does anyone have a mug with a handle on it? We have a lot of ones without handles. Oh, lovely. Can I steal it? Is there any beer in it? Excellent. Okay. Okay, so I put this here so we can see. Thank you so much. Okay, so I want to show you something that's going to happen. I'm going to show you a magic trick. I'm going to twist this 360 degrees, okay? I'm going to try not to break it. I'm sorry, Hermans, if I break it. Okay, so here we go. Twisting once. Watch the handles on this side. Okay, so I've twisted it once, but there's a problem, right? The object is back where it began, but the ambient space of my arm has all been twisted along with it. I'm going to now twist it a second time. So I've gone 360 and 720 degrees. The cup is back to where it began, and my arm is back to where it began. So let's do it one more time to make sure that you don't think I'm cheating you. Okay, 360 degrees, same direction, 720 degrees, 2 full rotations, and we've got back to where it began. Okay. Okay, but now I think we really do have to do it this way. This is as far as we're going today. We've brought out the underwear, we've brought out the pants, now we're bringing out the belt. Okay, let's take the same basic idea. I'm going to twist it half a rotation, 1 rotation, another half rotation, 2 full rotations, 720 degrees. I've twisted my belt, okay? Now, I am not going to, and I can do this, right? Topologists allow me to do that. That's not untwisting it. But one thing that I could do here is, okay, I have to be really careful so you don't believe I'm doing. All I'm going to change is my ambient space, how I grip it. I'm just going to come for a moment with my left hand here, and I'm just going to grip it here. I'm not changing the belt, right? I'm just shaking out my hand. And we pull it out, and the belt and all the loops are gone. So there's something really weird going on there, which is that when you twist something 360 degrees, the object returns to where it was, but the ambient space goes weird. And then if you go all the way to 720 degrees, it refreshes itself. And the physicists tell me that this is related to properties that actually happen in physics, specifically with something called spin 1/2 particles. And there's cool connections that I just believe them and think are interesting. I'm just an apologist. What do I know? You've been an amazing audience. I thank you so much, and I'm just here for a bunch of questions, but thank you so much for being a great audience. I'm sorry, it's a bit of a death trap, so I'll take the scissors at least.
Yeah, thank you so much for a very fun and educating evening. Please ask away.
Yeah, please, thank you. So what is a hole, really? Right, so I think my closest definition, and even here I'm going to slightly lie to you, is if it's a one-dimensional hole, you take a one-dimensional loop. And if it's missing the interior, I'll call that a one-dimensional hole. And our two-dimensional holes, I'll have to take a two-dimensional surface, like the surface of my balloon, and it encloses something missing. That's what I'll call a two-dimensional hole. So it is, in sense, the way I think of a hole is related to what the boundary of that hole is. If there is some boundary loop, and it's missing the thing on the inside, that is what I will call a hole. If my boundary is a two-dimensional thing, it becomes a two-dimensional hole. That's my notion of it. Yeah, please.
How old is topology as
Oh, very old. I guess it depends on where exactly you want to define it. Because depending on, let's say, the precision to which you prescribe the set of rules of which I'm talking about can really change what you're talking about. I mean, I would say that going back to the ancient Greeks, there are topics that are topological in nature. They're studying the nature of space with some allowed flexibility. In the last couple hundred years, though, is when there's been a real big explosion in tools in topology to justify it sort of given its own name, these algebraic tools that you can go and plug in and really calculate these invariants. That's much more recent, but a lot of the sort of larger ideas have gone back ages and ages, yeah. Yeah, please.
Thank you. Very.
Yeah, you're more than welcome.
Awesome. Can you give me an example of what you might use this for in everyday life right now?
Well, okay, maybe I won't say everyday life as in things as we're using as we go about our lives, but it is very useful in what we're doing in our society. So one thing that people are doing is called topological data analysis. And this is probably the biggest location of which I am aware of to which it is applied topology to solve problems in the real world. And basically the idea is a lot of the data sets that we now have, as you're scraping things together, whether it's neural networks, whether it's trying to look at very complicated systems, are extremely high dimensional. You'd have a data set that might be, for example, 10,000 dimensions, 10,000 degrees of freedom. And the goals of something like topological data analysis is to look at these things that are far beyond the sort of toy examples that we were doing here. You're trying to look at these objects that come to us from some sets of data and try to say, can I understand some of their structure? Can I understand some of their properties? Can I try and identify that a phenomenon has occurred in this data set, but not this data set because of these topological properties? So a lot of what sort of applied topology is focusing on being able to do sort of these computations in ways that you and I can't easily visualize it and imagine a pair of pants going into a different pair of pants. It has the idea that these are motivating examples for the tools, but the tools apply in these much higher dimensional spaces that have various applications sort of all around in terms of protein folding and all sorts of other fun stuff. Yeah.
I'm not sure if you covered this earlier, but is there such a thing as a three-dimensional hole?
Oh, there is, yes. And even some of the theorems I was saying, that Borshak-Ulam theorem, if you're on an n-dimensional sphere, okay, you have to imagine what that might be, and you want to mention n different properties, temperature, pressure, go on until n of them, you can do this as well. The thing about a three-dimensional hole is that, remember how a two-dimensional hole was you took the surface of the balloon and it was a thing, the three-dimensional volume inside that became a two-dimensional hole? To talk about three-dimensional holes, you have to be in the fourth dimension. So you need at least 4 dimensions to talk about objects of 3 dimensions, holes. Now, mathematicians love that, but I can't illustrate it as easily. But yes, there's 3-dimensional holes and an arbitrarily large number of holes, dimensional holes, yeah.
Does it work in both directions? Like, could you look at the history of the movement of the continent and work out the topology of the circulation in the same year?
Oh, so somehow you've sort of seen like a flow of the continents as that's moving along. And I'm sort of just riffing, but you could almost imagine that the topology that's formed might evolve as time. At some point, maybe there's a circle, an entirely trapped ocean, let's say. At some other time, it starts to split apart. Maybe there's some interesting ideas there. I'm not entirely sure. Although I will say that there is a branch of topology, something they call Morse theory, that really studies things that sound a little bit like what you're talking about. When you have objects that are evolving, you're trying to measure when precisely in their evolution do their topological properties start changing. That's absolutely something people try to measure and look at. Torsten, yes, lovely. Well, right, so the negative...
Added a hole and now there's nothing. So it said, okay, actually it had a 2-dimensional
Right,
hole
right.
already, but you added a 1-dimensional one.
That's right. So the idea of the balloon having a -1 holes was the lie of the talk, right? As in, when we first came about and saw it, we were trying to find something that seemed weird, like what do you mean by -1 holes? So what I'm saying is let's replace that answer with now we have a more sophisticated answer, which is what the balloon really has is a 2-dimensional hole. And when you add somehow this 1-dimensional hole, it really changes things. The 2-dimensional hole is gone entirely. It's now become a disk. We've lost everything. So, yeah. Yeah.
Is your universe 1-dimensional hole?
Well, it has to have a 0-dimensional hole. Remember I said everything's got a 0-dimensional hole.
Great. On that note, let's thank Dr. Trevor Bazett one last time.
Thank you so much. Thank you so much. Oh, thank you. Yeah. Yeah. That was sounds fun. Such a great audience, right?
Great idea.
And I only have.
Focus. There's only a few small pieces of
Yeah, that's.
I'll grab a piece down here.
I really got it popping not so egregiously when I was trying it.
And well, you know, whenever you do it in public, it's all completely different.
I know, yeah, exactly. This is whatever the scientific experiment is, then it's always going to be a bit different.